How was everybody? How was lunch? How was lunch? Like, without asking, somebody else came to me and said it was great, so good. Thanks to the Lido. Round of applause maybe for the great lunch. Where's Skylar to put up the next presentation, please, por favor. You want to go to the mic?
Sure.
Just a sec, I'll introduce you. Okay, next speaker is Tim Giesbrecht from Petronas, and his presentation is about the impacts of using gas mapping LiDAR in BC's first alt FMP program. So please join me introducing Tim, welcoming Tim.
Thank you. Thank you. Oh, geez. Not used to being on this side of the mic. Normally it's just me and questions. So yeah, thank you for the opportunity to speak today. Like I said, I'm with Petronas. People have been asking me lately, what do you do over there? Well, I'll answer it so I don't have to say it every time to everybody I know here, which is a good chunk of you. So I look after our fugitive emissions and methane profile. So that's everything from if it comes out of the pipe unexpectedly, what are we using to detect it, looking at the different technologies, and just ultimately looking at our fugitive emissions. So what I'm going to talk to you guys about today is about a technology that we've employed as part of our first alternative FEMP program. So I'll go over some definitions and we'll go from here. I think I got it. There we go. So just a little summary of what I'm going to talk to you guys about. We're going to go through some definitions just to get everybody on the same page. I know not everybody talks methane every day. I'm going to go over some kind of the drivers for why we're looking for methane reductions. And no, it's not just regulatory. There's other reasons too. Sorry guys, if you guys can't see me by my podium, I got my hype from my mom. So alternative FEMP, we're going to talk about what an alt FEMP is, and I'll give you the definitions of a FEMP, and then we're going to just kind of go over some of the performance that we've seen so far in our alt FEMP, and just some of the learnings we've had from this year's work. So methane, this is your CH4 molecule. It's also a potent greenhouse gas. It's also the main component of your natural gas. Here it says that it's 28 times more potent of a greenhouse gas than CO2. I think in the year and a half that I've been in this job, that number's changed from 25 to 28. So I suspect by, in the next 2 years, it'll be 32 times. So it's a moving figure. But it doesn't have the same kind of time scale with regards to lifespan in the atmosphere. So when they're looking at 100 times scale, it's 28. Well, when you shrink it to its, more of its lifespan of say 12 years, so on a 20-year scale, that number jumps to about 84 times. So fugitive emissions, these are an ex-convict methane molecules, but they are an unintentional release. So that it's something that's, let's say, escaped the pipe. So it's a fugitive, right? A FEMP is a fugitive emissions management plan. So if you hear me say FEMP, we like our acronyms here. You can see we got some videos going there as well. I'll go through those. But it's actually a regulatory requirement to have a written record on how we kind of detect, quantify, document our repairs, and ultimately just document our leaks. It's been a requirement since 2020, as Chris kind of alluded to in his presentation there yesterday. OGI, so optical gas imaging. If you look at the kind of grayscale imagery on my left, your right, that's kind of what we see through the camera. That's kind of in a high sensitivity mode, so that's using like a FLIR GF320 camera. The colored image, that's kind of like the modeling that you would see that's quantitative optical gas imaging. So it's using a technology where it's modeling that plume. As you can see, that green and blue, that's a color scale, and ultimately that's giving us an emission leak rate. So that's largely how we do our emissions. We don't send a lot of the gas molecules off into the lab and get an analysis. It's mostly quantified on site. So we call that OGI, and the other one's called COGI. So what's our drivers? Well, it's a regulatory requirement. So right now, currently, we have to do 3 times per year surveys at our facilities and compressor stations and your batteries, and then 1 time a year at your wells and your satellite batteries. So like Chris had mentioned, we're moving to 4 times a year in 2025 of doing an OGI survey. So that's our current regulatory requirement under the DPR. Repairs are supposed to be done within 30 days or in next shutdown. If it's at a well, it's 30 days. We're supposed to get that repaired in 30 days. Other drivers for us, though, is when I signed on to join Petronas, we had also just recently joined OGMP 2.0. So that's Oil and Gas Methane Partnership 2.0. So it's a United Nations environmental program where I think it's about 40% of the global supply of oil and natural gas is currently signed on as a signatory. And what it does is it's a voluntary initiative that shows that you're going to be working towards a reduction. So you set yourself a reduction target and a timeline, and it helps you basically improve your methane-informed or measurement-informed methane inventories. So within that, we have like an outline of kind of what our overall reduction targets are going to be. And it also aligns with Petronas' own internal net zero climate carbon emissions for 2050. So before I kind of tell you how well we're doing this year, I'll kind of tell you where we're at. So Chris's presentation, he kind of showed that we were aiming for a target of 45% reduction industry-wide from 2014 levels. So from 2020 to 2023, we've already seen a 40% reduction within Petronas. And so you can imagine from 2014 to 2020, we also had a reduction as we went and converted to low bleed pneumatics, instrument air packages. So we're seeing 40% reduction just from our 2020 time scale, which would already be less than what you would expect to see from a 2014 timeline. Our reduction efforts, when people go, well, what are you doing differently to get your reductions from 2020 to 2023? It's largely the leaks that we're finding these days are smaller, and we're fixing them quicker. So we had, in 2023 was our shortest time frame from leak detection to leak repair that we've recorded since having a FEMP program in 2020. That being said, our current FEMP program does have its own challenges. It's OpEx intensive. It requires a lot of resources. So annually, we would find about, say, 450 leaks annually between all those surveys that we were doing, which correlates to probably at least a 1-to-1 ratio, probably, so 450 to 500 work orders that are being pushed through our system, requiring repairs, services, shutdowns, outages. Often you find a leak and you repair it and it doesn't quite fix the problem, and you're out there again to try and fix it again. It says here, there's a large uncertainty in the emission rate measurements from the ground level. So you guys kind of saw that colorimetric profile there, the imagery. That typically has a plus or minus 30% accuracy. That's when in aggregate. So if you're looking at lots and lots of measurements, you might get that level of tolerance, which you can only imagine if our lab partners were giving us plus or minus 30%, you'd be a little concerned, I think, on your soils and waters. But on any given one measurement, you might find that it's out by orders of magnitude. So it can throw us for error, and these are the values that we have to work. Quantifying gas isn't easy. And again, just doing difficult to repair in 30 days. One thing that we're finding is that often the leaks that we are finding require some level of outage, so you have to kind of look at economic feasibility as to when you're gonna actually have time to take that system offline to do those repairs. So with that, we were like, okay, let's try and look at an alt FEMP. So an alternative FEMP is basically where it gives you the opportunity to circumvent or maybe stand down certain portions of the regulations as long as you can meet those reductions. So much like Chris, he teed me up perfectly by kind of outlining what would be the requirement for an alt FEMP. Basically, you gotta meet or exceed your emission reductions and show that you can do that with alternative technologies. So for us, we wanted to kind of focus our resources on kind of finding those largest emitting sources and reducing those. Since like 2021, we've tried out just about every type of technology there is to monitor methane at the source level, site level. So here's an example of a continuous monitor. So you can see that there's an anemometer. There we go. So you got your wind anemometer, you got your methane sensor, and there's this spot. It's basically a passive sampler where if the wind brings the methane to it, it'll get a detection. and you just have a solar panel, and it's using a cellular connection. So you'd put these around your facility. It uses like triangulation to kind of give you some localization, and then looking at the concentration, wind speed, local wind data, it would provide you a quantified value. As you can imagine, there's all kinds of false positives, false negatives, a lot of truthing with that. We've also tried like laser-based systems, like stationary systems. They don't work so good in fog, snow, wind, rain, line of sight. So we've tried a bunch of different technologies, and one of the technologies that we kind of landed on as being kind of a useful data set is Bridger Photonics gas mapping LiDAR. So kind of what does it work? I took this one right off their website because honestly it's pretty Greek to me, and they got a lot of smart people over there. But basically what it's using is a laser-based sensor mounted to a fixed-wing aircraft. For in our case, we're using like a Cessna 172. It's flying over our facilities at around between 500 and 700 feet above ground, and it's scanning a swath that gives us about a range of about 130 meters across our facilities. It does multiple paths. That laser is tuned to 651 nanometers, which if you're in the spectroscopy world, that's about, I think it's like 6,600 wave numbers. So it's in the infrared, but it's pretty close to the visible spectrum, but it's highly selective to methane, so you could have a propane leak. This technology is not gonna see it. So it's highly specific to methane. It doesn't see temperature. It does have its drawbacks, but it is, snow cover, standing water, smoke is now a realized thing. So it really kind of limits the number of days that we can actually perform the work. So with our alt-FEMP, we look to kind of do this during kind of the frost-free summer months. So why gas mapping LiDAR? Well, it has a really good objective probability of detection. So what we're talking about, probability of detection, it's defined. It's been studied ad nauseum with Carleton University. They're always looking at each iteration and generation of the technology to kind of prove like how low can they go. They've done lots of controlled releases here, I know, alongside with support from the BSER regulator. So they have a pretty good detection method. Right now, I think the current iteration of that sensor is around 1.3 kilograms per hour for the northeastern BC region is what they kind of determined. And it's dependent on a lot of different things. So they're looking at, what kind of impacts on that sensor is. So you have things from your altitude, like of a distance above ground, your localized wind speed. So the more data you have on your wind model, the more informed it is. And also like surface albedo, so like the reflectivity of the ground, because we ultimately have to get that signal to come back to the detector. So what you can see here is kind of what we would get as an actionable data set. I kind of have that there, and that's probably one of the key reasons why we also ultimately went with gas mapping LiDAR. It's something that I can actually do something with. You get 50 different continuous monitors pinging you saying, hey, you got a leak here, hey, you got a leak here, 24/7. After a while, you kind of don't start looking at those so much. And definitely ran into that, and then especially when you get a lot of false positives. So this is high selectivity for methane. It's helping us identify large sources. So in this example here, this is just a KML file that we would get with an overlay from the imagery, but you can see we have some incomplete combustion from the generators on this site, as well as some incomplete combustion from the compressor station, the exhaust. So I wasn't going to talk too much on numbers, but where would you think the bulk of our methane comes from in the oil and gas sector? Would you think it's from leaks? Well, it's not. On average, we're seeing about maybe 9% of our fugitive emissions is our total methane source, whereas 70% of our methane currently comes from incomplete combustion of lean burn engines. So with that, what's neat about this, or we're saying where there's bias to OGI, what you would find is that if you have an OGI technician, not necessarily they have an experience on understanding what controls you've put in place. So they might just see something and go, well, that's just a normal compressor seal vent. That's something that they would do, so we wouldn't monitor it. In this site in particular, for example, we identified these as fugitive emissions because we've actually put a seal pot in place, but the liquid level in the seal pot wasn't there. So we actually had gas escaping despite spending $6 million to not have it do that. So hence why that's our poster child in these photos. Similarly, the leak over on the left, I had actually done a survey at that site 2 weeks before this flight, and that wasn't leaking. So it had actually failed in between us doing an OGI survey and doing a follow-up LiDAR survey. And talking to our steam chief at this site, he went to me, he goes, that's a good one to find, he says, because that orifice meter, we were actually gonna take that out of our scope of work for our turnaround. And he's like, and I didn't want to, but now that it's failed, it has to go back in. And he says, if we had caught that after our turnaround, it would have been at least $50,000 a day in outage because we would have had to take the whole train down. But because we had a scheduled outage 2 weeks after this anyways, so well timing your flights with where you have your planned outages worked out really well. We got that repaired right away and it didn't have to have an unplanned outage. Another part that's really good about this, you can see there it says 100 sites per day. Twice this year, so we surveyed all of our wells and all of our facilities in this Q2 survey. So the data I'm going to show you is all from my second quarter work. And we were able to survey hundreds of sites in a day where with an OGI technician, you might get to 5 or 6 well pads in a day before you've houred out. So it's very effective. It's very comprehensive coverage. And it gives you a good data set where something I can do, perform a desktop review. So just even looking at the data from here that I would receive, I could look at this source and go, okay, I'm expecting that source, or no, hey, what is that source in the corner? So from that, we would look at like whether that source is intentional or unintentional. Flights are typically done over multiple days for anything that has a detection. You would follow up to confirm it, to kind of determine its intermittency or persistency of the source. All right, this is this one's gonna take a while. So what we did is in 2023, we surveyed all of our facilities as a voluntary initiative in hopes of supporting an alt-FEMP application to the regulator. So in 2023, we surveyed all our sites. And when I mean all our sites, I'm talking reclaimed sites, abandoned sites, suspended wells, literally every asset that we have in northeastern BC. I'm sure they were surveying clear over forests that you guys have long since reclaimed. We did everything just to see if we were going to see any emissions from inactive sites, much kind of like what we were seeing from Jordan's discussion yesterday. I'm happy to say that of the emissions that we found, aside from the odd surface casing vent flow at an inactive site, all of our emissions were at active sites only. So we used that from that data set. We looked at our emissions and compared it to our OGI surveys for the 3 surveys we had performed in 2023. And we used the probability of detection model, so for each of those technologies. So for OGI, Dan Zimmerle at Colorado University for METEC, they had created a probability detection model, which is essentially the red curve that I've created here for you guys, that was indicating the probability of detection of the standard OGI or a conventional OGI technician observing a leak. And we fitted this data actually once solving for these equations, and then vice versa, we have a probability of detection at 90% for Bridger Photonics for the northeastern BC region, and this was derived from Matt Johnson's group out of Carleton University. So we took those probability of detection models. I solved for X last Christmas on all these crazy equations, and then I fitted that data to what we had actually observed in 2023. So all this data has been normalized to the actual emissions that we attributed to fugitive sources from both LiDAR or gas mapping LiDAR and OGI. And what it presented here, I guess I'll just go through it. So this area in my far right is your A there, is areas where we were seeing leaks that OGI observed, but we didn't observe through LiDAR. And on the column here on the x-axis, you got your emission rates in kilograms per hour of methane and your probability of detection on the y-axis. So what we're seeing is that when the emissions are small, LiDAR doesn't see it, right? But OGI does. As you kind of get to a higher mark, so we're starting to see, at that 1 kilogram per hour, 1.3 kilograms per hour, we got a high likelihood that we're going to observe that emission. And there's certain instances where it's being also observed through OGI and LiDAR. So that's the kind of area B. And then some of those emissions that we're maybe seeing through LiDAR, could be due to just normal venting operations. So if we don't have good wind data, we have a really sheltered well site, you can, with gas mapping LiDAR, actually see just pneumatic venting that is operating within spec. It's doing what it's supposed to be doing, but just because of the nature of that teardrop site that's down in a hole, that's where we decided to build that well that day, we end up seeing emissions from that. So that's just the normal vented emissions. But then there's this large squishy area above here where we're saying leaks are detected by LiDAR and not by OGI. So what we're saying is essentially that there's certain portions of emissions that the LiDAR is seeing that we're not seeing through a conventional OGI survey. So this is what was really the premise for our alt-FEMP to meet that obligation that Chris discussed about meeting or exceeding methane reductions. So you add more tools, you can do more stuff, right? So adding another tool, we could see it more methane. So, I talk to my leadership and they go, what do you mean you're seeing more methane? Well, you gave me another tool, I found more methane. But it also gives us more opportunity for more reduction. So you have to quickly get that extra part in there, otherwise before they cut you off. So, that was our thing. So when you look at it as a net benefit, and I was looking at this graph last night and I thought, man, this is gonna be tough to explain, especially when it's a bunch of science. And then I thought, you know what, needs to be a Venn diagram. So I built this in here last night. So essentially what you got is your OGI, and where you have your overlap, that's your gas mapping LiDAR and OGI seeing it. There's a portion of your vented emissions that are being observed through gas mapping LiDAR. But all the space that, is here, that's essentially the methane that we're not seeing through a conventional OGI. So just what we had expected, this technology is good at finding us large sources, and literature has really shown through lots of studies that they're saying that, and through you'll see this in the EPA super emitter program, a good chunk of the methane that's emitted through a fugitive source is large and intermittent, or it's a sporadic source. So this is a really good way to detect it. So yeah, that's kind of what we're after, is trying to identify how big that is. Looking at the other curve, you can see that it's pretty squishy. That's the error bar associated with this work. So there is a high error bar in that quantification, especially when you're looking at a single pass. So much like OGI in aggregate gives you a kind of plus or minus 30%, a same kind of thing rings true for gas mapping LiDAR. There's a high variability, especially when you're looking at a single measurement. Maybe I'll just go back on that because I missed the one part. So in 2023, we did this. We took the data, looked at it. 2024, early 2024, we wrote an application to the BC Energy Regulator. And February 28th, we received approval to do BC's first alt-FEMP. So it's the first one that's been in BC. It's kind of nice to be first every once in a while. So what does that look like in terms of our survey comparison? So what I've kind of put here is our scope of work that we would typically be doing in the historical year. So we would have done a third-party OGI survey 3 times a year, depending on the infrastructure. But now for our alt-FEMP, we started in Q1, just doing as we would normally do. We did an alt-FEMP of all our compressor stations and gas plants. And then in Q2, which is where most of this work is coming out of, we did LiDAR of actually all our active and licensed sites, so all our well sites, all our compressor stations, gas plants, batteries. And then anything that we had a detection that we weren't sure about through a desktop review, got a follow-up. So we actually did 100% follow-up on any unknown sources. So if anyone's familiar with alt-FEMPs in Alberta, often they'll have a follow-up on an X percentage of sources. We opted to go do 100% follow-up on any source that was unknown. And then so in Q3 here, which we just wrapped up, we just did our LiDAR survey and we did follow-up on all of our compressor stations and gas plants. So what does that workflow kind of look like, and what's the advantage here? Well, because you realize we just internalized a lot of work. So typically what would happen is we would do a flight plan and schedule with Bridger. They would fly our sites. It typically took us about 20 days from initial flight to the final flights and getting reports. Meanwhile, you are getting reports fed to you in segments, like kind of weekly, so you can start performing some of your desktop review as you're getting that. So once we got our final report, that's me there, the subject matter expert, amongst others. We kind of tag team this because there was a lot of data, as you can imagine. So we're looking to see if the source is an intentional source, so incomplete combustion. The localization on this technology is really good, and if you have high-res imagery, you can pretty much see where your exhaust plume would be, and you go, okay, that's an intentional source. So then we would look for unintentional sources. From that, we would do a follow-up. Our follow-up on the 63 sources that we had to do took us roughly 34 days of field work from start to finish to verify all those sources. And on average, it took us about 45 days to do the repairs. So you can see we flew, cut off there a little bit, but we did 63 unique, or like facilities. So a lot of our facilities are co-located. We did roughly 430 well pads for 1,100 wells. Of that, we found 142 emission detections, and we had to do a desktop review. So here again, you'd see we're assessing whether it's incomplete combustion or fugitive emissions. So kind of as just a high-level summary, of those 142, we had 63 sources that we weren't sure about. Started looking at those, so that's roughly saying that we have about 80 lean burn engines running out there that we are known about. Of the 63, 44 were determined through internal OGI follow-up to be a fugitive source, and they accounted for 93% of those total emissions that were observed by LiDAR. So that's showing that using gas mapping LiDAR is an effective tool to not just find where all your exhaust stacks are, but also where you can find fugitive sources. So we found a significant part of our fugitive emissions from there. Part of our alt-FEMP application, when we went back and forth, it was like, hey, if you're going to travel to a well site and you're just going to check that one well, you should probably check all the wells. So we did. That was part of our approval process. So in doing so, we actually have performed OGI surveys at 15% of our wells. Between this and the commissioning work, so one of the other things that we do is that as we bring new wells on, it's a lot easier to find leaks before we actually get that into active production. So combining that work with this work, we've been able to survey 15% of our wells. So you're looking at like 180 of our wells have been surveyed to date. We drove about 4,700 kilometers to do all that work. Thanks to in-vehicle monitoring, it's not good just for telling you how fast you're going or if you're speeding. It also tells you how many kilometers you drive. On average, it took us about 19 days to do from detection to confirmation or a LiDAR follow-up through OGI. We were aiming for 14, but with getting your reports sequentially, it's pretty hard to do that considering it took us 20 days to get our final report. But overall, yeah, we had 4 employees doing this. We did quantification through a hierarchy of ground level quantification based on what we could. So if possible, we would actually use a PD meter to monitor failed pneumatics or something like that, which gas mapping LiDAR is really effective at identifying if you have an I2P transmitter or regulator that has failed. It really points it out really quickly. And then if not, we would use a high flow sampler, and for areas where we couldn't use the high flow sampler, we used that QOGI technology that you've seen previously. Yeah. So OGMP 2.0 reconciliation. So this graph here is basically showing in the light blue, it's kind of our top-down total. So what we call, when we talk reconciliation, we're comparing what we see from the sky versus what we have measured from the ground. So our light blue is our sky measurements, and you can see that we have a really good correlation between what we're seeing from LiDAR versus our stack testing at those incomplete combustion engines. And similarly for all the different components, even on surface casing vent flows and power generation and complete combustion, and even on fugitives, we're getting good correlation. So that's indicating to us that there's a high likelihood that we'll be able to reconcile our data set versus from the top down versus what our measurement informed inventory is from ground up. So when I'm saying L3, L4, that's all just OGMP talks of the level of hierarchies. But ultimately with the level 5, which is your top standard of OGMP 2.0, the idea is that you're going to use your top-down measurements to kind of better inform your inventory to see if you're missing methane or if you may be overestimating on certain aspects or over quantifying. But having good correlation across your different sources, or in our case we call these FEMP groups, indicates that we should have a good chance for reconciliation. Happy to say that when we looked in the aggregate across all of our assets using this 2023 data, our assets actually reconciled, which was a bit of a shock to all of us. So our top-down measurements lined up with our bottom-up measurements, which was great within the areas of uncertainty. So what was the learnings that we got from that? Alt-FEMP, it is good at detecting fugitive sources, especially some that we weren't seeing through conventional OGI surveys. It's an effective tool at the large sources especially, which is great because we want to focus on finding those large emitters and getting them under control. Scheduling the surveys during warmer months. So you saw that of the 63, the 44 were fugitives, so that means there was a handful that weren't. Some of those are due to just observations of like catalytic heat or maybe an incorrectly placed pin from gas mapping LiDAR that is actually incomplete combustion that's kind of just washed up against the building. The kind of plumes tend to stay together. So ultimately we want to be able to perform this work when our catadines are off so that we don't have that as a potential source popping up. It really sucks to drive to the end of the jetty just to find that a catadine's on. So yeah, utilizing a combination of these different technologies, we are going to be able to reduce our methane further than if we were just using a conventional FEMP program. With that, if you have any questions, now's your time to get back at me.
Well, it's not a question, but something to be aware of. You said it would be good to be first with something. You created another first today in the history of the producers meeting.
I did?
Yeah, you did.
Oh.
So Chris really wanted to see your presentation.
Okay.
So with the big help of the Lido, we set up a designated live link so we can watch the Victoria. You were live streamed.
Okay, there you go. So you just want to get back on questions. I get it.
Well,
sorry.
There's a reason why we do it. Now we cannot ask questions.
Yeah, yeah.
Sorry. Questions from the audience?
Great presentation, Tim. Just have a question with the reference from LiDAR to OGI. So in the POD curves,
Yep.
Your classification with D, what sources are you contributing that are identified between those two?
So D would have been, that's your gas, so that would have been a source that was attributed as an unintentional source through LiDAR, where when we did a follow-up, we didn't have a correlating OGI emission that we could correlate that to. So it wasn't seen through our conventional surveys when we were out there, but we found that source only through using that technology, right? So that's the piece, that's the chunk of the puzzle that we're hoping to find, knowing that there's larger sources that might be, a lot of them, I mean, even in 2024, it's compressor seals, right? You know, as we put seal pots, yeah, Kate's nodding, she knows, it's not just us, right? But finding those systems where they're maybe not operating as intended, you know, or if you have like a failed VRU, those kinds of things is what we're typically finding as those sources. But it's helping us identify where we need to be, what's our bad actors, what we need to work on. And so if we can shrink that big part of that bubble down, that's all reductions. And I mean, you know, whether you would have to cast that backwards into inventory, probably because lots of times our compressors didn't have compressor seals in 2014. So those emissions would have been there. So they should be part of that inventory, whether they were measured that accurately in 2014. But that's ultimately what that source is. Yeah, we're finding it from basically things that were not getting reported through an OGI survey. Pneumatics that are ripping out of there, that maybe a guy goes, well, I think that's normal, maybe that's just a high bleed device, and it's not, it's a failed regulator, right? Yeah.
And just one more question in regards to catadine heaters. Now, contributing source, just curious why not including it within the time frame or months, right? Obviously, there's winter conditions with that, but just curious, is that a contributing source to your overall emissions there?
Yeah, so why to do the surveys when they're off? Yeah, so our measured, our methane inventory would be done on an L3 emission factor, or assuming a percentage of oxidation, knowing that those aren't very efficient. So it's kind of as an L3 measurement because it's not a material source for us. So it's not something that we're necessarily going to look to high grade. That being said, it's probably a project for 2025 because we're seeing it there more. So just not to have it populate so that we can better identify when it's actually a leak. So like going to a site just to find that your DI has the door open and 3 catadines going in the reboiler. Yeah, Kate knows exactly what I'm talking about. But you see that and then you go, oh, okay, that's what it is. Like, so this last round of surveys, I suspected I was going to run into it because I was in there in October. So I prioritized all of my emissions based off of what I thought was like, I really don't know what that is. That's most definitely a problem. And then you'd look at it and go, okay, they were able to see it with LiDAR, but maybe not quantify it, or if they did quantify it, it was like 5, and it was just about always at 5 meters height, which tends to be the height of a building. You would almost indefinitely find that the source that you were seeing was just the accumulation of catadine incomplete combustion coming out the side of the building.
Awesome. Thank you.
Yeah, you bet.
Any other questions?
Great stuff, Tim. With this additional data, I guess you're probably putting it into an asset management program, so you're tracking these repairs?
Yep.
And with the additional data, is this going to help you with a preventative maintenance program so you can be more proactive?
Yeah, so you see, we're big on the FEMP group, and I'm going to steal my boss's, rather than doing what he would say called whack-a-mole, you see a leak, you fix it, you see a leak, you fix it, you see a leak. We really try and categorize it and try and find what the root cause is. And I'm not an engineer, but I get to work with a lot of them. And the big thing is if you can engineer that control right out, or if we got to find a better solution, or if we're finding that, hey, we're having a recurring bad PVRV, that's what we want to really look at so that we can try and find the root cause and then just eliminate those out of our systems, right? So yeah, big part. So this year, it might be a knowledge-based thing on informing our operators on what's expected on running a compressor seal and making sure that your seal pot's full, right? Yeah. So yeah, absolutely it is.
Great presentation, Tim.
Thank you.
Is there an elephant in the room here that you've exposed with the methane releasing in atmosphere being greater than 95% from poor combustion versus the low number of fugitive emissions?
So you saw that I asked, if you were here yesterday, I asked Chris a little bit about, what are we going to do with incomplete combustion? So incomplete combustion, without a doubt, is our largest methane source in the oil and gas sector. There is some operators that are convenient enough that they can do electrification. For us, that's still something that we're looking at, but for us, it's a dominant source. One thing that you'll run into, MZAPA regulations ran in, which maybe Chris didn't allude to, but when MZAPA regulations came in, it was to reduce NOx. So one of the ways to reduce NOx was to convert rich burn engines to lean burn engines, but inherently what happened is you created a methane problem. So they actually, we're having a struggle here. Do we want lower NOx or do we want lower methane? There is some solutions on the market for some engines where you can essentially have a lean burn engine converted to a rich burn engine, so you can get lower NOx and low methane. So like a Waukesha 744 Series 5 would be an example. Caterpillar currently doesn't have a solution for that, so when half your fleet's a Caterpillar 3608 or 3612 or 3616s, we typically see that those are quite elevated methane, and we don't really have an answer. But to your question, Joffrey, when I first started here at Petronas, it was like Canadian federal regulations was like, we're going to get all engines under to 1 kilogram per hour, or per kilowatt hour. And by December of that year, I saw a federal release where it was like, we're going to address that through MZAPA regulations at a later date, because I think they realize there isn't really a solution. Yeah.
So Bridger flights,
Yes.
recognizing that you're flying BCR is flying, we're flying all over the same sites.
Yeah.
Like, I thought about this for a while. There's only so many days between like May and August where we want to be flying. Like, is there an opportunity to get together and better utilize that? Like, we're chasing fugitive emissions and then flying av fuel over the same sites 8
Yeah.
times. Like, it seems a little crazy.
Yes, so that's a great opportunity. I would probably suggest you talk to somebody at Carleton University about methane net. I'm only just a little bit involved, but from what I understand, that is ultimately what we're trying to do to try and better understand basically BC's and Alberta's methane intensity as a whole. And one of the things is to have signatories sign on as part of methane net to help support that information. And nice thing about it is it's kind of being independently done through a university. I know we've been working to try and get some level of what that looks like, and we're trying to help get that off the ground. But absolutely, that is a way to collaborate. As for like going directly from Bridger and working with your account manager, I think it's a little harder for them to do flight plans across that way, because it's like, we're gonna do Tim's site and then we're gonna do Kate's site and we're gonna jump over, that would be a little difficult, because I've actually had the pleasure of seeing how they would do some of those flight plans, and they actually have to look at topography. It doesn't sound like a fun job, just to do that. So like correlating from us to you directly, no, but if by coordinating our services, they're very much a Costco, right? It's a bulk-based discount. So the more sites you do, the cheaper it is, right?
Totally, yeah. And maybe Tourmaline and Petronas could just buy an airplane and do it ourselves.
That's right, yeah.
We can take that offline.
Yeah, sure.
Well, I was just wondering, is there an option to use drones for it?
Yeah, good question. So, Petronas being a global player, obviously we've talked to, and with being OGMP 2.0, ultimately we're going to need L5 measurements for all of our assets, and a significant part of our assets are actually offshore. So, the idea of standing water doesn't really work well, right, for Bridger. So they are working currently as a technology to put that on a drone, specifically for offshore. But yes, there is an opportunity. And they have even put it on helicopters. And what is unique about kind of like what we were seeing yesterday through Jordan's presentation, his detection was actually much lower than what we're seeing, right? Because I'm at about 46 cubes per day was kind of my detection limit at P90, and he's reporting at 1 cube a day, right? So, but when you go to a helicopter, like in California, because a lot of their stuff is very stationary, high density, they tend to do it with a helicopter, and it actually quite drops their detection limit, partly because they're flying at a lower altitude, and I think they're just getting more chances at a scan for a detection. Yeah.
Anybody else? Thank you, Tim. Very informative.
Thank you.
Before I introduce the next speaker, just wondering if you guys want to have the break this afternoon or continue and skip it. We'll put some snacks and everything in the back so you can grab as you go, but so people can drive safely home when it's daylight. So show a hand if you're in favor. Opposed? Motion approved. Okay, so we keep going then. Are the people from WorkSafe BC here? They're not back yet, so we may have to short break anyway. We'll see. They should come back from the local office. Next speaker, Kristen Zorb, BC Energy Regulator, and she will give a core update. You have a presentation?
I did, yeah. All right. Can I have a presentation?
He's putting it up.
Okay. Oh, there I am. Okay, which one?